An interesting effect of induction is something called back EMF that you get in motors. At the top left, you see a motor with a coil spinning in the magnetic field because the current-carrying coil is experiencing a force. However, we now know that if a coil turns in a magnetic field, there must be a changing flux through the coil, and so EMF is going to be generated. According to Lenz's law, of course, the EMF must be in the opposite direction to the supply voltage. So the net voltage now is the supply voltage minus the EMF. We can then use Ohm's law, but instead of having simply the supply voltage, we have to subtract the value of the back EMF. The thing to note is that the size of the back EMF depends on the rate of turn of the coil. So it's zero when a motor starts, but then it increases gradually as the motor speeds up. Now on to eddy currents. We know that if we had a metal loop, as in the top right, and pulled it out of a magnetic field, there would be a current induced because the flux through that loop is decreasing. This still works even if it isn't a ring of wire but is a metal sheet instead, as you can see on the left. What we call eddy currents can build up anywhere in a sheet of metal. They're called eddies because they are like little whirlpools of current. They build up and then die down quickly in a metal. So if we pull a sheet of metal out of a magnetic field, the area that is leaving the field will have reduced flux through it. So it creates eddy currents around the edge of the field that will make more magnetic flux to oppose the change. In the picture, you see flux into the screen decreasing, so the current moves clockwise to make more flux into the screen. Eddy currents can be made to be useful to us, as in this case where we have electromagnetic braking. Have a look at this metal disc spinning anti-clockwise as we look at it from the top. A magnetic field acts through one section of the disc, and it points downwards. Think about the part of the disc entering the magnetic field. The flux downwards through it is increasing, so an eddy current is formed that creates some field upwards. The upwards field is shown as the blue arrow, and the direction of the current loop causing that is in red. If we look at how the part of the current loop that is inside the magnetic field interacts with the field, we use the right-hand rule with the current moving away from us and the magnetic field downwards. Then the force on the disc will be to the left, which is clockwise. It's the same with the part of the disc leaving the magnetic field. An eddy current loop is formed in the opposite direction on that side, and it interacts with the field to make another force pushing clockwise. So that combined force acts to slow the disc down.